In this problem, they're asking us to consider the effect of adding a strong species to different solutions, some of which are buffered. And the point is to illustrate the effect of buffering. In part A, it's an interesting scenario. We've got a weak acid, propanoic, whose Ka value is 10 to the minus fifth. But we're adding to that the strong acid, hydrochloric acid. Of those two, the strong acid is way, way, way more important in determining pH. The K value of hydrochloric would be roughly infinity. So this one is actually easy to solve. All we need to do is take negative log of the hydrogen concentration, and the hydrogen concentration would just be whatever amount of hydrogen provided by the strong acid, in this case 0.029 moles, and they tell us that we have a volume of 1 liter. So if we work that out, it's 1.54. B is a much more interesting problem. Here we've got a salt that contains a conjugate base of the weak acid. And so we have some absorbing ability with this one. I like to draw a picture of the reaction vessel and list all the species broken apart if they're strong electrolytes. So we've got the strong acid listed as broken apart hydrogen and hydroxide. We've got the salt, which, because all salts are strong electrolytes, would break apart as well, as sodium and propanoate. And then, of course, as with all aqueous solutions, we've got water. Here we've got a strong species, hydrogen ion, which wants to react with the best base available to it. Well, if we survey the other substances, we can cross out chloride ion because it's the conjugate of a strong species. We can cross out sodium because it's a metal that doesn't have a high enough charge to be of any importance. And we've got the conjugate base of the weak acid, which would be important, and water. Of those two, the K value for the conjugate base of the weak acid is going to be way bigger, and therefore the more important one in determining pH. We'll set up a reaction to completion equation and table with those two species reacting. And with reaction to completion tables, we're not tracking initial changes and equilibrium. We're just tracking what happens before and after the reaction. And rather than working it out in units of moles, we're going to work it out in units, instead of units of molarity, we're going to work it out in units of moles. So if we just check the problem carefully, we can see that they gave us 0.029 moles of the strong acid. So we'll note that in the before and after table, 0.029. And in part B, they say we've got 0.1 molar sodium propanoate. So propanoate has a concentration of 0.1, and it's in a 1 liter reaction vessel. So 0.1 times 1 gives 0.1 moles. They don't mention any propanoic acid, so we get a 0 moles initial concentration for that one. To fill out the afterline of this table, one of the two reactants will go completely down to 0, and it's going to be the one that has the lower number of moles. Hydrogen only has 0.029 moles, and the propanoate ion has more at 0.1. But the propanoate ion is going to go down by the same amount. If 0.1 is reduced by 0.029, you get 0.071, just as 0.029 went down to 0. On the other side of the equation, we'll see an increase by the same amount, 0.029, to give us, if you start at 0 and add 0.029, then you have 0.029. At this point, we have the numbers of moles of the species after the reaction to completion, and we can identify an acid. We've got the weak acid, propanoic acid, and we have its conjugate base, propanoate ion. If you have at least some acid and some base, we can write the Henderson-Hasselbalch equation and find the pH very quickly. pH equals pKa plus the log of the ratio of base concentration over acid concentration. The Ka value they gave us is 1.3 times 10 to the negative fifth. And now that we've identified the acid and the base, we can just divide one by the other. Don't be concerned that the number of moles isn't the same as the molarity. Since they're in the same reaction vessel, that ratio of moles will be exactly the same as the ratio of the molarity. So we'll just keep going. 4.886 for the pKa and 0.389 for the other. We just add the two together and get 5.275 for the pH. Part C of this problem is a lot like Part A. We only have pure water and we're adding a strong acid to it. So to get the pH, it's as simple as taking the negative log of the hydrogen concentration, which would be contributed to almost entirely by the strong acid. Water does contribute some of the hydrogen. It contributes a very small amount. Remember, water's K value is 10 to the negative 14th. Compare that to a K value of infinity in the case of hydrochloric acid. So to get pH, we just take negative log of 0.029, and we get the same answer as we did in Part A, 1.54. So in this problem, parts A and C are very similar, and parts B and D are going to be very similar. I'll record the answers we've gotten so far. 1.54, 5.275, 1.54 again. And then in part D, we'll make this part D. Once again, I like to draw the reaction vessel and all of the species in it. So we've got a strong acid, hydrochloric, which would exist as broken apart once it's dissolved. And in part D, we have the weak acid, propanoic, as well as the salt, sodium propanoate, which would exist as broken apart because salts are strong electrolytes. And of course, with any aqueous species, we have water. Hydrogen is a strong species. It's a strong acid species, which means it will react with the best base available to it. If we look at the other substances in this reaction vessel, chloride will not be a good partner for hydrogen because it's the conjugate of a strong species. The weak acid is not going to partner with hydrogen because it's also an acid. A strong acid doesn't also want to react with a weak acid. The metal ion, sodium, is not good because its charge isn't high enough to be acidic, or in any case, two positive ions wouldn't interact. They would repel each other. We're left with either water or propanoate ion. The K value for water is very small, 10 to the minus 14th. The K value for propanoate ion will be something much bigger. We don't need to know it, but you could find it by taking Kw divided by the Ka value that they gave us, and just eyeballing it, you would say, okay, Kw is on the order of 10 to the negative 14th, and the Ka value that they gave us for propanoic acid was on the order of 10 to the minus 5th. So I would expect the K value for propanoate ion to be on the order of 10 to the minus 9th, roughly. Since we have a strong species, we'll write an equation for a reaction to completion. And as acids donate protons and bases accept protons, we reform some of the propanoic acid. So we'll actually be adding to its concentration as we keep track of it. Before and after or reaction to completion tables are kept track of in units of moles rather than molarity, as we did with ice tables. So we'll read the problem carefully to see what those numbers of moles are. They gave us up at the top that the number of moles of hydrogen ion dropped into solution is 0.029. They tell us in part D that we have a 0.1 molar concentration of propanoic acid in a 1 liter solution. So 0.1 times 1 gives us an initial number of moles of 0.1. And then lastly, we have 0.1 molar sodium propanoate in a 1 liter solution. So again, we would find that by taking 0.1 times 1 and get 0.1. One of the two reactants will react all the way down to 0. And in this case, it's going to be hydrogen. The propanoate ion is going to go down by the same amount, down by 0.029. That gives you a final number of moles of 0.071. And on the other side of the equation, rather than going down, we'll see an increase by the same amount, 0.029. So if we take 0.1 and add 0.029 to it, we have 0.129. These are all numbers of moles. Now we've got a nice accounting for all of the species that exist after the reaction to completion. We have the conjugate base of a weak acid, and we have the weak acid. Since we have at least some acid and base, we can use the Henderson-Hasselbalch equation to find pH. The Ka value they gave us up at the top, 1.3 times 10 to the negative fifth. Oops. And we'll take the base number of moles over the acid number of moles. .129 for the acid. And if we crunch those numbers, we get 4.886 for the pKa, just like we found in part B. And for the other portion of the expression, negative 0.259. And if you add that together, we get 4.627.